No.
Hello, good afternoon, everyone. Welcome to the first talk session of the AGM GCPR 2020. We are going to start now with 5 talks. There will be 2 long orals and 3 spotlight presentations. The first presenter is Dmitrij Sitenko. He is going to present assignment flow for order-constrained OCT segmentation. Please go ahead.
Okay. Oops. Thank you for the kind introduction. So today I will present the recent work on the assignment flow for order-constrained OCT segmentation, which is driven by medical image applications such as in the field of detection of retinal eye diseases. This is the joint work with Bastian Boll and Christoph Schnörr. I begin the presentation by first giving a short introduction into the optical coherence tomography imaging. So each OCT volume is generated by acquiring a single A-scan orthogonal to retina ordering axis, which is depicted by the yellow bar, and which is moved within the direction of a blue plane, generating multiple A-scans, which together assemble a single B-scan, and the home process is repeated into the B-scan axis, and as a result from the backscattered light, we obtain an intensity valued OCT volume, and our goal is to partition this OCT volume into regions of interest, which in our case are the specific retinal tissues. And this is an important task for medical applications for detection of pathological patterns within human retinal tissue and for diagnosis of diseases like glaucoma. By taking a closer look on the problem, we encounter the following difficulties. So first, we have a low signal-to-noise ratio as depicted by the left box, which is caused by the presence of speckle noise from the scanning process. We have shadow regions with missing information depicted by the right box because of the presence of vessel structure within the data. And the third point, we must respect the biological ordering of human retinal tissues during the segmentation. And these difficulties were tackled by recent approaches, which I shortly review next. So the first method was proposed by Dufour et al., and which uses a graphical model and incorporates hard and soft constraints for respecting the ordering of human retinal tissues during the segmentation. Another method was proposed by Radke et al., who employs a probabilistic graphical model and models retinal tissue boundaries by using a low-range Gaussian shape prior. Our contribution in this work is that we use local features for retinal classification. We have a local regularization during the segmentation process. We incorporate only the prior knowledge of biological order of the retinal tissues without using any shape prior. And this work is an extension of the method proposed by Freddy Aström and Christoph Schnörr to ordered assignments. Now I briefly introduce the assignment flow. So the basic idea of the assignment flow is the probabilistic view of assignments. So we consider the assignments of the labels to the nodes of a graph by discrete probability distributions living in probability simplex, which we equip with a Fischer-Rao metric and turn it into a Riemannian manifold. And to consider the interactions of the nodes together, we define the product space of these probability simplices, which we denote as the assignment manifold. As input to the assignment flow, we have a distance matrix, which encodes the data term and which can be computed, assembled by in any feature space with equipped with a metric. We have a pixel neighborhoods at each node to control the interaction. We have a lifting map, which defines the likelihood map, which we use to lift the data to the assignment manifold. And we have an approximation of the Riemannian mean given by the similarity map. And which acts like a regularizer within our model. And we let the assignments evolve on the assignment manifold by following the Riemannian flow, which we initialize at each node by the barycenter. And at each integration step, we compute the similarity map and the likelihood map, which gives us a coherent direction of evolution of assignments to a unique labeling. To adapt the assignment flow to give us ordering labelings, we explicitly derived the feasible set of pairwise ordered assignments for a single A-scan given by the following set. And we use this information and incorporate it on the assignment manifold by using a smooth barrier function, which penalizes the deviation from the current assignment to the pairwise ordered assignments by decreasing the parameter gamma. And this allows us again to define an energy functional for a single A-scan, which is explicitly parameterized on the assignment manifold. And we use this information and sum over all A-scans within the 3D volume and define the global energy which we want to minimize. And the minimization process is performed by geometric integration on the assignment manifold proposed by Ruben Hühnerbein, and where we use the generalized likelihood map to lift the gradient and the distance in the data term to the assignment manifold, and integrating the flow gives us a special regularization supported by A-scan ordering of retinal tissues. We proceed by to our two choices of feature spaces to assemble the distance matrix. So the first choice is given by the set of symmetric positive definite matrices, which is a Riemannian manifold equipped with Riemannian metric at each point on the tangent space, and the Riemannian distance has the following explicit expression. So to lift the data to this Riemannian manifold, we extracted each voxel first and second order derivatives, which we subsequently assemble by using the covariance region descriptor and adding some regularization, small regularization parameter epsilon. And we minimize the k-means like functional to obtain representative clusters for each retinal tissue. And the distance matrix is finally assembled by approximated the Riemannian distance by the Stein divergence for faster and more efficient computation. The second choice of features which we propose is given by convolutional neuronal net features, and we rely on the ResNet architecture where we train this model by only using as input a small window centered around each voxel. So we have a small field of view to keep the locality, and we use the predicted score as a distance matrix by simply reversing the sign of the predicted score. And if we consider the results, so on the left picture, you observe a raw B-scan taken from a 3D volume. In the middle, you observe the score predicted by trained ResNet, which is unordered. And if we post-process this result by integrating the ordered assignment flow, we obtain the following accurate segmentation, which is ordered of the human retinal tissues. So we proceed with the results. Here you observe a B-scan, and on the right side you observe annotated segmentation by a medical expert, which serves as ground truth. And if we now use the covariance region descriptor and compute the distance matrix after local rounding, at each voxel we obtain the following noisy and unregularized segmentation. If we only use the basic assignment flow on the right side, we observe spatial regularization, but with violating ordering constraint. And if we now use the ordered assignment flow and decrease the parameter gamma, we obtain more accurate and ordered segmentation. And finally, using the predicted score from ResNet, we obtain following accurate segmentation of human retina. So in summary, what we have proposed is 3D segmentation model for detection of human retinal tissue within volumetric data. The benefits of our approach is the spatial regularization, which leads to smooth transition of retinal boundaries. And our method is scalable and can be implemented on a GPU. And we have ordered segmentation by only incorporating prior knowledge of biological retina ordering, so without using any shape prior, which makes this method amenable to extend it to detection of pathological patterns within human retinal tissues, which is the future work. Thank you for your attention, and now it's time for questions.
Thank you, Dmitrij. Before we move on to the questions, I would like to remind everyone that we have a Discord channel that you can find on the conference website. Please click that purple button if you want to ask questions to the speakers. There is one question. Is it possible in the assignment flow framework to loosen the ordering constraint?
So we have a global energy functional, and we include the gradient on the assignment manifold. So during the integration, we have only soft constraints. So when we integrate, so it's still possible if we stop the integration that we have some violation of the ordering because it's a soft constraint. By decreasing the parameter, we obtain higher regularization. So we adjusted the parameter such that it gives us ordered segmentations.
Okay. There are no more questions coming from the audience, so I would like to ask one question. Could you comment on the computational complexity of your model?
So for the underlying distance matrices, so for covariance region descriptor and ResNet, the computation time takes around of 20-30 seconds for 3D volume of dimensions 460 times 560 times 61. So it needs only 20-30 seconds.
Okay.
For the home segmentation.
Okay. Thank you. Let's move to the second oral presentation. This is going to be delivered by Abdelhak Lemkhenter, and the title of the talk is On the Importance of Learning the Phase-Amplitude Coupling in Biosignal Classification. We will have 12 minutes of talk, and 3 minutes of questions.
So hello, everybody. Today we'll be presenting our work on boosting generalization in biosignal classification by leveraging the phase-amplitude coupling. This work was done by Professor Favaro and me, Abdelhak Lemkhenter at Bernt University. When it comes to biosignals, supervised learning is very challenging in the sense that manual annotation is rather expensive since it requires the input of experts and neurologs. And also, even if you have access to such annotation, there are a lot of factors of variation within the data that can be subject dependent or hardware dependent, and the labels themselves can be quite noisy. For example, when it comes to sleep scoring, the average human agreement is around 83%. And even if you suppose that you have access to some huge data set like ImageNet, for example, but the equivalent for biosignals, then you might not necessarily be able to transfer what you learn on that dataset to your target task because that dataset may not share the same electrodes or data modalities. So what can we do instead? Instead, we propose to learn useful feature representation without labels. More precisely, we propose to use self-supervised learning, which refers to the framework where we train a model, typically a neural network, on an artificial task for which the labels can be generated automatically. For example, on images, we could define the task as solving a jigsaw puzzle, which we can always generate in an automated fashion. Our main contribution is a novel self-supervised task for biosignals, which we call phase swap. And we draw inspiration for this task from two different facts. First, most of the handcrafted features used for biosignal classification rely on the power spectrum of the signal. More generally, they compute the power within certain predefined frequency bands at the expense of discarding the phase information. On the other hand, we know from various medical studies that the phase information is correlated to various cognitive functions within the brain. So because of that, we define the following phase swap operator. Given two time series segments, x1 and x2, we compute their Fourier transform x1 hat and x2 hat. Then we take the amplitude information from x1 and the phase information from x2 and generate a new synthetic time series XPS. And we define the task as the following. We train a neural network to discriminate between real examples, x1 and x2 here, and synthetic ones, XPS. The hope is that by training a network on this task, it will learn the natural coupling between the phase and amplitude information. And in order for this task to be useful for downstream classification problems, it needs to satisfy two properties. It needs to be semantically relevant, as we stated before. Certain medical research papers have shown that the phase contains relevant information, and it also needs to be non-trivial. So here we have two examples of signals, x0 and x2, and we also show different combinations of those two signals by either taking the phase from x2 or from x0. As you can see on the four figures, there's no obvious pattern or artifact that would allow you to easily spot which one is the real one and which one is the synthetic one. For evaluation purposes, we choose to fine-tune our features on downstream tasks. So we start by an encoder network, followed by a linear classifier, and that we train on the self-supervised task. Then once that training is finished, we remove the last layer of the network and replace it with a linear classifier for the supervised training, and then train both networks jointly with a lower learning rate. Note that we use the same data for both the self-supervised learning and supervised learning. However, the window size for the two might be different. And for evaluation purposes, we use the balanced accuracy as our main metric, since most problems we will be tackling suffer from class imbalance. And we will be evaluating on three different sets: the validation set, which shares subject identities and recording sessions with the training set; test set A, which differs from the training set in terms of recording session, but has the same subject identities; and test set B, which differs in terms of subject identities and recording sessions. So the first evaluation we do is on the sleep cassette dataset, which is part of the expanded sleep EDF database, which contains 78 different identities with 2 recording each. And the task on this dataset is a classification task for determining the current sleep stage. We do our evaluation for different values of our train, which refers to the ratio of identities used for training. And as you can see on the table, for both testset A and testset B, the model pre-trained on the phase swap self-supervised task outperforms its supervised counterpart by a margin of at least 3%, which means that the features learned through the self-supervised task are more robust and generalize better to new recordings and also new subjects. We also wanted to highlight how well this self-supervised learned features fare when the test subjects are different from the training subjects in terms of pathologies. So for that, we use the ISRUC sleep dataset, which contains three different subgroups. Subgroup 1 and 2 contain respectively 110 subjects which suffer from sleep disorders, and subgroup 3 contains 10 different healthy subjects. As you can see on this table here, for the for testset B, which has the same nature of pathologies as the training sets, all patients have the sleep disorders. We get a slight improvement in terms of balanced accuracy. However, we get an even bigger improvement on subgroup 3 because the supervised baseline, or at least our main hypothesis, is that the supervised baseline has learned features that are too specific to the sleep disorders that are present in the training set, whereas the phase swap pre-train allows it to learn more general purpose features. We also evaluate our model on 2 additional datasets. The first one is the sleep telemetry dataset, which is very similar to the sleep cassette before. And we obtain also very comparable result to the previous experiment with an increase of accuracy of around 8% on both testset A and testset B. We also try to test our framework on a different type of problem, which is seizure detection. So we did this on the CHB MIT dataset. And unfortunately, we can see on this table that the phase swap pre-training doesn't help improve the performance. And this can be explained by the fact that the task, the self-supervised one, seems to be trivial on this dataset, because we can see that the validation accuracy for the self-supervised learning is above 99%. So instead, in order to make the task more challenging, we add a form of random masking where we keep 6 out of the 24 channels, out of the 18 channels used on this dataset at random. And with this masking, the task is then non-trivial, and we can see again an improvement of generalization on both testset A and testset B. Our hypothesis on why this is the case is because the CHB MIT dataset contains a larger spatial resolution when it comes to brain activity. So the phase content of the signal has both a spatial and temporal component. However, our phase swap operator only modifies the phase in the temporal domain and doesn't rectify the phase in the spatial domain, which leads probably to artifacts that are very easy for the network to spot. This is further supported by the fact that masking helps, which means that by restricting the spatial resolution of the model, it is able to learn better features. We also compare our phase swap self-supervised training to another self-supervised method present in the literature, which is called relative positioning, in which the task is defined as determining whether a pair of 2 signal windows are nearby temporally or not. And we show that this task doesn't have the same benefit in terms of generalization as our task. As you can see on the table, computed on the sleep cassette dataset, we're still the model trained on the pre-trained on the phase swap self-supervised learning task, denoted here by PS, is the top line, whereas the one trained on the relative positioning task is comparable to just the supervised baseline. So there's no additional benefit of using that. Last but not least, we also show that our pre-training or the benefit of our pre-training is not dependent on the architecture choice. So for all previous experiments that I've shown so far, we used FCN, which is a simple convolutional neural network architecture that has been shown to be a strong baseline for time series classification. Instead, in this experiment, we replace it with a deeper, more powerful ResNet architecture, and we test it on the sleep cassette dataset. And as you can see on this table here, the performance on both testset A and testset B is better when phase swap is used, and that for different values of the window used during the pre-training and for different values of the R-train. So all in all, we have shown that self-supervised learning is a very promising framework for learning useful features for biosignals, because it's fairly inexpensive to add to any pre-existing training pipeline, and it is not very specific to the data modality choice or the architecture or the task. We have shown that it works for EEG, EMG data, or body temperature, on both sleep scoring and seizure detection. And we have shown also that it provides quite a significant boost in terms of generalization to new settings. Thank you for your attention, and we will provide the code very soon on the following link.
Thank you, Abdelhak, for a very interesting presentation. So I have one question. This is an interesting way to see how a data augmentation mechanism that works for images or visual data works for other modalities as well. And I was wondering if other types of augmentations like cropping or blurring the signal would work for audio signals as well, or have you had the chance to try other augmentations?
Well, the main idea of the phase swap works a bit differently than a data augmentation, because when you're using a data augmentation, you want your features to be invariant to whatever data augmentation you're using. However, for self-supervised learning, you want the model to be covariant to those augmentations. So you want to detect whether the phase was swapped or not.
Mm-hmm. I see. Okay. Okay, so if there are any other questions, please feel free to post them in the Discord channel. You can find the link to the Discord channel of this talk from the program of the conference. I see that there are some people typing. I will wait for 1 minute for one of those questions to arrive. Okay, so one question is there something analogous to contrastive learning used in ImageNet for biosignals?
You could think of this as a form of contrastive learning, because in the end, what is contrastive learning? It's defining a pair of positive segments and a pair of negative segments and trying to draw the positive elements closer to each other and push the negative segments away from each other. Here, we define the positive relationship as just being a clean signal and the negative one as being a signal for which the phase was corrupted.
Okay, thank you. So thank you, Abdelhak, for very interesting presentation. We can move to the next speaker now. We are going to start short orals now, spotlight presentations. The first one is going to be delivered by Saurabh Sharma. The title of the talk is Long-Tailed Recognition Using Class-Balanced Experts. Please go ahead.
Hi, good afternoon. So this is our work on long-tailed recognition using class-balanced experts. So the problem is, given a long-tailed training set, we maximize a 4-fold accuracy on a balanced test set for the following classes, namely many shot classes that have more than 100 images, and medium shot classes that have between 100 and 20 images, and few shot classes that have less than 20 images, and all classes. So for instance, here is the data set distribution for ImageNet LT. This data set was proposed in the CVPR 19 paper by Liu et al. So it has a really imbalanced class distribution with a lot of many short classes and with a lot of few short and medium short classes, and some many short classes that account for most of the examples. So the key challenges in this problem are relative imbalance between the many short classes and the few short classes, and data scarcity for the rare classes that are that we call few short classes. So our approach consists of an ensemble of class balanced experts. So we take the long-tailed data set and split it into 3 approximately balanced class balanced subsets of many short, medium short, and few short data. And for each subset, we train an expert model. Each expert model has a reject class that accounts for all the classes in the other 2 subsets. And we initialize each expert model with a baseline model that is trained on the entire long-tail data set. And this allows us to transfer knowledge from the many short classes to the medium short and few short classes in a very straightforward manner. And we don't need to resort to memory-based models or complicated loss objectives. So this is a very simple and effective strategy. Our inference proceeds as follows. So we feed our test example through each of the expert models, and each expert model gives us logit scores corresponding to the classes that each expert is trained for. We concatenate these logit scores and get an uncalibrated posterior, which means that these 3 experts can have different amounts of confidence on their predictions. So we must do a joint calibration. So we learn scale and shift parameters. So the scale parameters are multiplied element wise with the posterior, and we add the shift parameters to that, and we take a softmax and we get our calibrated posterior. And so we learn the scale and shift parameters on the validation set, and we use this inference module on our test set. So this gives us our best results. And so our main experiments consist of an oracle upper bound, firstly. So we assume that we have oracle access to the ground truth expert for each test sample. And this basically gives us an upper bound. So we find that the oracle upper bound basically allows us to match the medium short and few short accuracy to the many short accuracy on both ImageNet and Places LT, which suggests that data scarcity is not the bottleneck, but instead it's a relative imbalance that is a harder problem, because the data scarcity for few short and medium short classes does not prevent us from pushing the accuracy as high as the many short classes. And furthermore, we compare our approach with the state of the art. So we have two ensembles, the first one consisting of our class balanced experts, and the second one where we make our ensemble more bigger and diverse by adding these classic approaches for long tail recognition, such as uniform class sampling, GAN-based augmentation, and the approach by Liu et al. And this gives us state-of-the-art results, and the expert ensemble alone allows us to reach close to state-of-the-art on ImageNet and Places LT. So in summary, we showed that our simple and effective approach allows us to reach close to state-of-the-art results, and our oracle upper bound shows that relative imbalance is harder than data scarcity. So that's it for my presentation.
Thank you, Saurabh. I was wondering, why do you think the accuracy improvement doesn't reflect to the many shot classes? You have accuracy improvements on the low shot and few shot classes, but the many shot results didn't improve in some cases. Why might that be?
So I believe that is because we already have sufficient data for the many shot classes, and none of the approaches that we tried with was able to improve beyond that. It's basically because it's already saturated, and whatever we do to improve few shot actually reduces the many shot accuracy.
So it's a trade-off.
Yeah.
Okay. Thank you for the presentation. We can move to the next speaker now. Just to remind everyone that you can ask questions at any time to the speakers from the Discord channels, and you can find them from the main conference website. Our next speaker is Yue Fan. He's going to talk about analyzing the dependency of ConvNets on spatial information. You can go ahead.
Okay. Thank you for the very nice introduction. So hello everyone. It's my pleasure to present this work here, analyzing the dependency of ConvNets on spatial information. So this is a joint work with Dr. Xian Yongqin, Max Losch, and Professor Bernt Schiele from MPI Informatics. Okay, so in this work, we investigate the necessity of spatial information in convolutional neural networks, and we find that spatial information at deep layers is not really necessary for a good classification accuracy. So I'll start with a very interesting experiment. Let's say now we have a very typical classification problem, and we just design a model like this, and then we just train our model. Let's add something different here. So at each training iteration, we just take this feature map here before the next convolution, and then we randomly shuffle the activations on the feature map spatially, and then we will get this guy here. And this random spatial shuffle is independent across feature maps and training steps. So now the question would be, how will this random spatial shuffle influence the final performance? So we train a VGG16 on CFAR 10. And this is the architecture, and this is the training curve. The x-axis is the number of epochs, and the y-axis is the test accuracy. This is just a standard training and test. So the model can eventually get 94% test accuracy. So now keeping the rest of setup the same, we apply the random spatial shuffle to the last three conv layers here, both at training time and at test time. And this is our result. So surprisingly, the curves here looks very similar to the curves over here, and the shuffled model also reaches 94% test accuracy in the end, which means that this random spatial shuffle doesn't really influence the final performance nor the training process. And now let's make it more systematic, because here we only apply the random spatial shuffle to the last three layers here, what if we apply to the last 4 layers, last 5 layers, or even last 10 layers? So now we're going to draw a different plot here. The x-axis here is the number of shuffle layers from the last, and y-axis is still the test accuracy. And this dot here represents the baseline performance because the baseline has 0 shuffle layer. So now we shuffle the last layer here, and then we train our model, we test it, we have a new dot here. And then we shuffle the last 2 layers, we have a new dot here, and then we do the same for the last 3 layers, last 4 layers, until all layers being shuffled. So we can basically have a curve like this. And as we can see here, the more layers we shuffle, the worse the performance is. But we should also notice that the baseline performance is actually kept for a really long time. So for example, with even last 7 layer being shuffled, we still have the baseline performance. So it seems that the random spatial shuffle at deep layers doesn't really harm the test accuracy. And this phenomenon can be verified across architectures and data sets. And here I want to do a comparison between a random spatial shuffle and random channel shuffle. And this random channel shuffle means that instead of dispositions on feature maps, we shuffle the order of the feature maps. So here we still have the same plot. X-axis is the percent of shuffle layer from the last, and y-axis is test accuracy. The blue curve we have already seen, and the green curve is basically the one from the channel-wise shuffle. And we can see that the green curve drops much faster than the blue curve with the increase of shuffle layer from the last, which indicates that the model is not really robust against the absence of channel-wise information, but the model is indeed robust to the missing of spatial information. So now we can reach the conclusion that spatial information at deep layers is not really necessary for a good test accuracy. And now here I want to show some detection result on VOC dataset. Here we use a YOLO model, and we only shuffle the last layer inside the backbone. And this is the architecture, and the backbone is just a ResNet 50, and we have a detection head like this. And to avoid pre-training a shuffle model on ImageNet, we here compare a standard model and a shuffle model, both trained from scratch. And the baseline has MAP 50 and 50%, and the shuffle model has a 34% MAP. And in order to understand this performance difference, we adopt the diagnosis tool from Hoing, which is basically classifies the model prediction into 4 categories. Prediction is correct if it has correct label and the IOU is greater than 0.5. And the prediction is a localization error if the label is correct, but the IOU is in between 0.1 and 0.5. And it is a wrong class if the label is wrong and the IOU is greater than 0.1. And it is a background error if the IOU is completely like the bounding box is completely off, the IOU is smaller than 0.1. And here we have the diagnosis result from the baseline and the one from the shuffle model. We can see that in terms of background and wrong class error, they're actually more or less the same, but this localization error is actually doubled here. That's why we have this performance difference. While shuffle model has more localization error, it actually has the same classification accuracy as the baseline model. Because if you compare the percentage of the blue color, they're actually the same because the both correct and localization error have the correct label. And now here I want to show some qualitative results from the baseline and the shuffle model. You can see that actually the bounding box from the shuffle model is not completely off, but the model is definitely not good at localizing the small object. For example, this bus here and these 3 people on the board. So to conclude, in this paper, we found that spatial information at deep layers is not really necessary for a good classification accuracy, and random spatial shuffle harms the localization of small object in detection task. With that, I conclude my presentation. Thank you very much for your attention.
Thank you, Johan, for an interesting presentation. We have a question that also is shared by multiple people. For low resolution images of size 32 by 32, you showed that spatial information can be deleted from later layers with small accuracy drops, right? How would this observation be different for higher resolution images? Will the spatial information be more important in the same later layers then, since the receptive field will have covered only a smaller proportion of the image?
Yes, very good question. That's actually true, because we also tried this thing on the ImageNet dataset, and we found that actually the number of the number of the unnecessary leader layer is like much less than what we have on CFR 10 dataset.
Mm-hmm. Okay, good. Okay, so we are out of time a little bit. I would like to thank you again for your presentation. And now we can move to the last spotlight talk of the session. It's going to be delivered by Lukas Koestler. And the title of the talk is Learning Monocular 3D Vehicle Detection Without 3D Bounding Box Labels. You can go ahead, Lukas.
Okay. Thank you very much. My name is Lukas Koestler, and I'm excited to present Learning Monocular 3D Vehicle Detection Without 3D Bounding Box Labels. This is joint work with Nan Yang, Wang, and Cremers. Training 3D object detectors requires large datasets with 3D bounding box labels for supervision. We aim to overcome the need for manual labeling, which has also been tackled in prior work. Non-learning methods that optimize an energy function for individual vehicles do not require bounding box labels because no training is involved. These methods can deliver strong results, but are unable to leverage data through learning. On the other hand, previous work on label-less learning-based 3D object detection has either focused exclusively on the stereo setting or used label-less loss functions together with bounding box labels for supervision. In contrast, we present the first monocular 3D vehicle detection model that can be trained without 3D bounding box labels. Next, we explain our network architecture and training procedure that enable label-less learning. Our architecture is based on pseudo-LiDAR. A pre-trained image-to-depth network predicts a depth map from the input image. The depth map is then back-projected into a point cloud. Afterward, a predicted segmentation mask is used to define objects. For each object, the object point cloud is processed by a frustum pointer that predicts position, orientation, and shape. We encode the shape using a shape manifold of meshes with fixed topology. The deformed vertex positions are given as the sum of two terms. First, the mean vertex positions are the vertex positions of the mesh corresponding to an average car. Second, the shape coefficients are multiplied by the corresponding vertex displacement matrices. For end-to-end training, we use a recent implementation of OpenDR to differentiably render the predicted mesh. Our single image network uses two loss functions. The segmentation loss compares the rendered segmentation mask to the input segmentation mask. The chamfer distance measures the distance between the predicted mesh and the object point cloud in 3D. Because our model does not use bounding box labels for learning, we leverage pre-trained networks. For instance segmentation, we use mask-RCNN, which is pre-trained on COCO. We evaluate the model using 4 different image-to-depth methods. The learning-based methods are pre-trained on Kitty, using either LiDAR data or self-supervision. We also extend the model to temporarily consecutive frames, which requires ego and object motion estimation. Please refer to the paper for details. We evaluate our model on Kitty against 2 methods that require 3D bounding box labels for training. The proposed method achieves promising performance in comparison to MonoGRNet, which is a state-of-the-art monocular object detector. The comparison with Mono3D shows that training without 3D bounding box labels is feasible and delivers superior performance to this common baseline. Due to the pseudo-LiDAR architecture, our model can use depth maps from any image-to-depth algorithm. For example, we use depth maps from MonoDepth2, which is a self-supervised mono-to-depth network. In this case, our entire pipeline, including the pre-trained networks, does not require supervision on Kitty. Unsurprisingly, the performance of this model is worse in comparison to using depth maps from the supervised BTS. However, we still achieve better results than Mono3D, despite not using any labels on Kitty. Our method was developed for monocular 3D object detection, but by using depth maps from GANet, it can directly generalize to the stereo setting. Stereo RCNN delivers superior results to our stereo model, but it is specifically designed for stereo images and additionally uses some 3D bounding box information during training. Please consider our paper for additional details. Interestingly, our stereo model shows better performance than direct shape. We argue that this is because our model can leverage training dataset through learning. Please visit our project website for more information, and thank you for your attention. And now I would be happy to take any questions.
Thank you. So I was wondering if, since you don't use ground truth bounding boxes, but make use of the pre-trained networks, during that transfer, was there any specific observations that you had that may not have affected the performance of your model?
What do you mean by specific observations that have not affected the performance?
Were there generalization problems, or did your model have to recover from partial detections or things like that?
Oh, yes. So as you might have seen from the results, generally the results are much better for easy cars, which are also not occluded, and are worse for moderate and hard cars, which are occluded. And this is because then, for example, the segmentation loss isn't as well defined. So I would say generally in the setting where you don't train on exactly the loss function that you want to minimize in the end, so the distance to the 3D bounding box, it might be that the surrogate loss function, for example, the segmentation loss, is still decreasing on the training and even the validation set, but at the same time, the loss you're really interested in, the difference to the bounding box, is actually going up. So stabilizing the training was one of the major challenges, I would say.
Mm-hmm. Okay, thank you. So at the moment, we don't have any questions from the Discord channel, but we have actually a discussion session starting now. In case any of the audience would like to discuss one-to-one with any of the authors of this session, please join the Discord channel, and you can join the talks, #talks1, and also you can ask questions via audio to the authors. I would like to invite all the authors to join the Discord channel, and in case there are any questions asked to them, please discuss the details of your papers. I would like to also thank all the authors who have presented in this session. If you could turn on your videos again, that would be nice to see all of you again. Thank you for your contributions, and let's continue with the discussion now. Bye.